Hello everyone. In previous class, we discussed about what is summing amplifier, differential amplifier and instrumentation amplifiers. पिछले वाली क्लास में हमने ये तीन ऑपरेशनल एम्पलीफायर के बारे में स्टडी किया था, जिसमें समिंग एम्पलीफायर हमने पढ़ा था। उसके बाद हमने डिफरेंशियल एम्पलीफायर स्टडी किया था। आफ्टर दिस हमने स्टडी किया था इंस्ट्रूमेंटेशन एम्पलीफायर। Now in this lecture we will study about what is the integrator amplifier, its circuit diagram, its working. After this we will move the next topic is the differentiator amplifier. इसके अंदर हम इसका सर्किट डायग्राम देखेंगे, क्या होता है, कैसे काम करता है, ये हम स्टडी करेंगे। नेक्स्ट टॉपिक इज लॉग एंड एंटी लॉग एम्पलीफायर। इसके बारे में भी हम डिटेल में पढ़ेंगे कि क्या लॉग और क्या एंटी लॉग एम्पलीफायर होते हैं और कैसे ये काम करते हैं। एंड फाइनली द रेफरेंसेस ऑफ दिस प्रेजेंटेशन। सो इन दिस लेक्चर वी कवर ऑल दिस टॉपिक वन बाय वन। सो लेट्स स्टार्ट विद टॉपिक 1, द इंटीग्रेटर एम्पलीफायर। So first question is that what is integrator amplifier? The integrator operational amplifier, in short op amps, produce an output voltage that is both proportional to the amplitude and duration of the input signal. The operational amplifiers can be used as part of a positive or negative feedback amplifier or as an adder or subtractor type circuit using just pure resistance in both the input and the feedback loops. But what if we were to change the purely resistance or resistive RF feedback element of an inverting amplifier with an frequency dependent components or frequency dependent complex element that has a reactance X such as a capacitance C? What would be the effect on the operational amplifier voltage gain transfer function over its frequency range as a result of this complex impedance? By replacing this feedback resistance with a capacitor, we now have an RC network connected across the operational amplifier feedback path, producing another type of operational amplifier circuit commonly called as operational amplifier integrator सर्किट। तो इंटीग्रेटर सर्किट हम कैसे बना सकते हैं? जो हमारा फीडबैक रेजिस्टेंस है RF, अगर उसको हम रिप्लेस कर दें रिएक्टेंस X में, तो हमारा एक नया टाइप का एम्पलीफायर बनके हमें मिलता है, जिसको हम बोलते हैं ऑपरेशनल एम्पलीफायर इंटीग्रेटेड सर्किट। So what is the integrator circuit? As its name implies that operational amplifier integrator is an operational amplifier circuit that performs the mathematical operation of the integration. That is, we can cause the output of respond to change in the input voltage over time, as the operational integrator produced an output voltage which is proportional to the integral of the input voltage. So this is the circuit diagram for the integrator amplifier circuit. इसमें हमने फीडबैक रेजिस्टेंस की जगह यहाँ पे कैपेसिटेंस का यूज किया है, RF की जगह C का यूज किया है, जिससे कि जो हमारा नया सर्किट डेवलप होता है उसको हम बोलते हैं इंटीग्रेटर operational amplifier circuit. In other words, the magnitude of the output signal is determined by the length of the time a voltage is present at its input as the current through the feedback loop charges or discharges the capacitor as the required negative feedback occur through the capacitor. When a step voltage Vin is firstly applied to the input of an integrating amplifier, the uncharged capacitor C has very little resistance and act as a bit like a short circuit, allowing maximum current to flow by the input resistor RL. as potential difference exists between the two plates. No current flow into the amplifier inputs, and the point X is a virtual arc resulting in the zero output. As the impedance of the capacitor at this point is very low, the gain ratio of Xc by Rm is also very small, giving an overall voltage gain or less than 1. As the feedback capacitor C is being charged up due to the influence of the input voltage, its impedance Xc slowly increases in proportional to its rate of charge. The capacitor charges up at a rate determined by the RC time constant tau of the series RC network, जो आप लोगों ने नेटवर्क में जैसे निकाला है, सिमिलरली हम इसमें टाइम कांस्टेंट tau को फाइंड आउट करेंगे. The negative feedback force the operational amplifier to produce an output voltage that maintain the virtual arc at the operational amplifier's inverting inputs. Since the capacitor is connected between the operational amplifier's inverting input, which is at a virtual ground potential, and the operational amplifier's output, which is now negative, the potential voltage Vc developed across the capacitor slowly increases, causing the charging current to the decreases as the impedance of the capacitor increase. This results in the ratio of Xc by Rm increasing, producing a linearly increasing ramp output voltage that continued to increase until the capacitor is fully charged. At this point, the capacitor acts as an open circuit and blocking any overflow of DC current. The ratio of feedback capacitor of input resistor is Xc divided by Rm is now infinite, resulting in infinite gain. The result of this high gain is that the output of the amplifier goes into the saturation as shown in a figure. Saturation occurs when the output voltage of the amplifier swing heavily to one voltage supply rail or the other with little or no control in between. So this is the input signal and output signal waveforms. The rate at which the output voltage increase is determined by the value of the resistor and the capacitor RC time constant. By changing this RC time constant value either by changing the value of capacitor or the value of resistor, the time in which it takes the output voltage to reach saturation can also be changed. तो सैचुरेशन कैसे चेंज हो सकती है अगर हम आरसी टाइम कांस्टेंट को चेंज करें. आरसी टाइम कांस्टेंट हम कैसे चेंज कर सकते हैं, या तो सी की वैल्यू चेंज करके या फिर आर की वैल्यू को चेंज करके. फॉर एग्जांपल इफ वी अप्लाई a constantly changing input signal such as a square wave to the input of the integrator amplifier, then the capacitor will charge and discharge in response to change in the input signal. This results in the output signal being that of sawtooth waveform, whose output is affected by the RC time constant of the resistor capacitor combinations because of high frequencies. The capacitor has less time of fully charged. This type of circuit is also known as the ramp generator, and transfer function is given below. So next is a ramp generator. Operational amplifier integrator ramp generator. We know from first principle that the voltage on the plates of the capacitor is equal to the charge on the capacitor divided by its capacitance, giving Q by C. Then the voltage across the capacitor is output V out, therefore V out is equal to Q by C. If the capacitor is charging and discharging, the rate of change of voltage across the capacitor is given as. So this is the rate of charge of voltage across the capacitor. So the value of Vc is equal to Q by C, and Vc is equal to Vx minus of Vout, or we can say that 0 minus of Vout. So dV out by dt minus dVi by dt is equal to dq divided by C dt, or we can say that 1 upon C dq by dt. But dq by dt is the electric current, and since the node voltage of the integrating operational amplifier at its inverting input terminal is 0, so the value of x is equal to 0, and the input current I flowing through the input resistor Rn is given as In is equal to Vn minus of 0 divided by Rn, so we get Vn by Rn. The current flowing through the feedback capacitor C is given by If is equal to C into dV out by dt, so we can write the equation C into dq by C dt, or we can write dq by dt, or is equal to dV out C divided by dt. Assuming that the input impedance of the operational amplifier is infinite, ideal operational amplifier, no current flow into the operational amplifier terminals. Therefore, the nodal equation at the inverting input terminal is given as In is equal to If, or we can say that I is equal to Vn by Rn is equal to dV out into C divided by dt. So Vn divided by V out into dt divided by Rn into C is equal to 1. From which we derive an ideal voltage output for the operational amplifier integrator as V out is equal to minus of 1 upon Rn into C integration 0 to t Vn into dt. So we can rewrite the equation is equal to minus of integration 0 to t Vn dt divided by Rn into C. To simplify the maths a little, this can also be rewrite as V out is equal to minus of 1 upon j omega into Rc into Vn, where omega is equal to 2 pi f and the output voltage V out is a constant 1 upon Rc times the integral of the input voltage Vn with respect to the time. Thus, the circuit has the transfer function of an inverting integrator with a gain constant of 1 upon Rc. The minus sign indicates 180 degree phase shift because the input signal is connected directly to the inverting input terminal of the operational amplifier. The AC and continuous operational amplifier integrator, if we change the above square wave input signal to that of the sine wave of varying frequency, the operational amplifier integrator perform less like an integrators and being to behave more like an active low pass filter, passing low frequency signal while attenuating the high frequency. At zero frequency or DC, the capacitor acts like as an open circuit due to its reactance, thus blocking any output voltage feedback. As a result, very little negative feedback is provided from the output back to the input of the amplifier. Therefore, with just a single capacitor C in the feedback path at the zero frequency, the operational amplifier is effectively connected as a normal open loop amplifier with very high open loop gain. This results in the operational amplifier become unstable, causes undesirable output voltage conditions and possible voltage rate saturation. This circuit connects a high value resistance in parallel with continuously changing or continuously charging and discharging capacitor. The addition of this feedback resistor R2 across the capacitor C given the circuit the characteristics of an inverting amplifier with finite closed loop voltage gain, which is given by R2 by Ra. The result is at high frequencies the capacitor short out this feedback resistor R2 due to the effect of capacitive reactance reducing the amplifier gain. At the normal operating frequencies the circuit acts as an standard integrator, and while at a very low frequency approaching 0 Hz when C become open circuit due to its reactance. The magnitude of the voltage gain is limited and controlled by the ratio of R2 by R. Unlike the DC integrator amplifier above, whose output voltage at any instant will be the integral of a waveform, so that when the input is a square wave, then the output waveform will be triangle, shown in a figure. For an AC integrator, the sinusoidal input waveform will produce another sine wave as its output, which will be 90 degree out of phases with the input producing a cosine waves. Furthermore, when the input is triangular, then the output waveform is also sinusoidal. This then forms the basic of our active low pass filter. So the DC voltage gain of integrator amplifier circuit is equal to AV naught is equal to minus of R2 by R1. AC voltage gain AV is equal to minus of R2 by R1 into 1 upon bracket 1 plus 2 pi f C R2. Corner frequency F naught is equal to 1 upon 2 pi C into R2. In the next tutorial or next slide about the operational amplifier, we will look at the another type of the operational amplifier circuit, which is the opposite or complement of the operational amplifier integrator circuit above, called the differentiator amplifier. तो इसी का जो नेक्स्ट स्लाइड में हम पढ़ने वाले हैं वो डिफरेंशिएटर एम्पलीफायर सर्किट पढ़ेंगे, जो कि इंटीग्रेटर का जस्ट अपोजिट है, या हम उसको कॉम्प्लीमेंट भी बोल सकते हैं. As its name implies, the differentiator amplifier produces an output signal which is the mathematical operation of differentiation, that is it produced a voltage output which is proportional to the input voltage, rate of change and the current flowing through the input capacitor. Second topic is the differentiator amplifier. The basic operational amplifier differentiator circuit produces an output signal which is the first derivative of the input signal. Here, the position of the capacitor and the resistor has been reversed, and now the reactance XC is connected to the input terminal of the inverting amplifier, while the resistor RF forms the negative feedback element across the operational amplifier as normal. The operational amplifier circuit performs the mathematical operation of differentiation, that is, produce a voltage output which is directly proportional to the input voltage rate of change with respect to the time. In other words, the faster or the larger the capacitor to the input voltage signal, the greater the input current, the greater will be the output voltage change in response, becoming more of a spike in shape. As with the integrator circuit, we have a resistor and the capacitor forming an RC network across the operational amplifier, and the reactance XC of the capacitor plays a major role in the performing of operational amplifier differentiator. तो ये जो डिफरेंशिएटर एम्पलीफायर होता है ये इंटीग्रेटर का जस्ट अपोजिट होता है, या हम कॉम्प्लीमेंट भी बोल सकते हैं, कॉम्प्लीमेंट ऑफ इंटीग्रेटर एम्पलीफायर. So this is the circuit diagram for differentiator ऑपरेशनल एम्पलीफायर. इसमें हम क्या करते हैं, इसमें जो हमने कैपेसिटर और आरसी नेटवर्क जो फॉर्म किया है वो हमने इन्वर्टिंग इनपुट के साइड फॉर्म किया है, जबकि हमने इंटीग्रेटर में क्या किया था, फीडबैक पाथ में हमने आरसी नेटवर्क फॉर्म किया था. तो यही दोनों में बेसिक सा डिफरेंस है. तो ये हमें डिफरेंशिएट करके देता है आउटपुट में, और इंटीग्रेटर सर्किट हमें इंटीग्रेट करके देता है आउटपुट सिग्नल. सो द इनपुट सिग्नल to the differentiator is applied to the capacitor. The capacitor blocks any DC current or any DC content, so there is no current flow to the amplifier summing point X, resulting in zero output voltage. The capacitor only allows AC types input voltage change to pass through the whose frequency depends on the rate of change of input signal. At low frequencies, the reactance of the capacitor is high, resulting in a low gain, means RF by XC, and the low output voltage from the operational amplifier. At the high frequency, the reactance of the capacitor is much lower, resulting in a high gain and higher output voltage from the differentiator amplifier. However, at a high frequency, an operational amplifier differentiator circuit become unstable and will start to oscillate. This is due to mainly the first order effect, which determines the frequency response of the operational amplifier circuit, causing a second order response, which at a high frequencies gives an output voltage for higher than what would be expected. To avoid this, the high frequency gain of the circuits need to be reduced by adding an additional small value of the capacitor across the feedback resistor RF. Okay, so same maths to explain what's going on. Since the node voltage of the operational amplifier and its inverting input terminal is 0, the current I flowing through the capacitor will be given as IN is equal to IF, or we can say that IF is equal to minus of V out divided by RF. The charge on the capacitor equal capacitance times voltage across the capacitor. So Q is equal to C into V. Thus, the rate of change of this charge is dq by dt is equal to C dVn by dt. But dq by dt is the capacitor current I, so the IN is equal to C dVn by dt is equal to IF, or we can say that minus of V out divided by RF is equal to C into dVn by dt, from which we have an ideal voltage output. The operational amplifier differentiator is given as V out is equal to minus of RF into C dVn by dt. Therefore, the output voltage V out is a constant minus of RF into C times the derivative of the input voltage Vn with respect to the time. The minus sign indicates a 180-degree phase shift because the input signal is connected to the inverting input terminal of the operational amplifier. One final point to mention: the operational amplifier differentiator circuit in its basic form has two main disadvantages compared to the previous operational amplifier integrator circuit. One is that it suffers from instability at the high frequency as mentioned above, and the other is that the capacitive input makes it very susceptible to random noise signal, and any noise or harmonics present in the source circuit will be amplified more than the input signal itself. This is because the output is proportional to the slope of the input voltage, so some means of limiting the bandwidth in order to achieve the closed loop stability is required. If we apply a constantly changing signal such as a square wave, triangular or sine wave type signal to the input of the differentiator amplifier circuit, that resultant output signal will be changed and whose final slope is depending upon the RC time constant of the resistor and the capacitor combination. So this is the input signal and this is the output signal. Input signal is the first one is a square wave, second triangular, and third one is a sine wave. Now next is the improved operational amplifier differentiator. The basic single resistor and single capacitor operational amplifier differentiator circuit is not widely used to reform the mathematically function of differentiation because of two inherent faults mentioned above, instability and denoise. So, in order to reduce the overall closed loop gain of the circuit as the high frequencies and extra resistor are in, is added to the input as shown in a figure. So this is the improved operational amplifier differentiator circuit. इसमें हमने एक एडिशनल आर इन रजिस्टर को इनपुट में ऐड कर दिया है। इससे ऐड करने से क्या है, जो हमारे दो ड्रॉबैक्स हैं उनको हम मिनिमाइज कर सकते हैं और एलिमिनेट कर सकते हैं। Adding the input register Rn limits the differentiator increase in the gain at the ratio of Rf divided by Rn. The circuit now acts like as a differentiator amplifier at low frequencies and an amplifier with resistive feedback at the high frequency, giving much better noise reduction. Additional attenuation of high frequency is accomplished by connecting a capacitor CF in the parallel with the differentiator feedback resistor RF. This then forms a basis of active high pass filter as we have seen before in the filter section. तो इम्प्रूव्ड करने के लिए हमने क्या किया है, इनपुट में एक आर एन रेजिस्टेंस जो है वो कनेक्ट किया है और फीडबैक में हमने एक सी एफ कैपेसिटर को आर एफ के साथ पैरेलल पे कनेक्ट कर दिया है। तो इससे जो हमारे दोनों प्रॉब्लम थी उसको हमने एलिमिनेट कर दिया। सो नंबर नेक्स्ट इज अ लॉग एंड एंटी-लॉग एम्पलीफायर सर्किट। The electronic circuits which perform the mathematical operations such as logarithmic and anti-logarithmic with an amplification are called as logarithmic amplifier and anti-logarithmic amplifier respectively. So first one is called the log amplifier. The log amplifier is an electronic circuit that produces an output that is proportional to the logarithmic of the applied inputs. An operational amplifier based on logarithmic amplifier produces a voltage at the output which is proportional to the logarithmic of the voltage applied to the resistor connected to its inverting terminal. The circuit diagram of an operational amplifier based on log amplifier is shown in a figure. This is the circuit diagram for log amplifier. इनपुट में हमने एक रेजिस्टेंस R1 को कनेक्ट किया हुआ है और आउटपुट में और फीडबैक में एक हमने डायोड को कनेक्ट किया हुआ है। In the above circuit, the non-inverting input terminal of the operational amplifier is connected to ground. This means 0 volt is applied to the non-inverting input terminal of the operational amplifier. According to the virtual short concept, the voltage at the inverting input terminals of the operational amplifier will equal to the voltage at its non-inverting input terminal, so that the voltage at the inverting input terminal will be 0 volt. So the nodal equation at the inverting input terminals node is 0 minus V1 divided by R1 plus IF is equal to 0. So we get the value of IF is equal to VI divided by R1. This is equation number 1. The following is the equations of the current flowing through a diode when it is forward biased. So the IF is equal to IS into E to the power minus of VF divided by NVT. This is the equation 2, where IS is the saturation current of the diode, VF is the voltage drop across the diode when it is in forward bias, VT is the diode thermal equivalent voltage. Now the KVL equation around the feedback loop of the operational amplifier will be 0 minus VF minus V0 is equal to 0. So Vf is equal to minus of V0. Substituting the value of Vf in equation number 2, then we get IF is equal to IS e to the power minus of V0 divided by N into Vt. This is equation 3. Observe that the left hand side terms of both the equation 1 and equation 3 are same. Hence, equate the right hand side terms of those two equations are so below. So Vi divided by R1 is equal to Is into e to the power minus of V naught divided by n into Vt. Applying natural logarithm on both the sides, so we get log n Vi divided by R1 into Is is equal to minus of V naught divided by n into Vt. So finally we get Vt or V naught is equal to minus of n Vt into log Vi divided by R1 into Is. Note that the above equations, the parameters n, Vt and Is are constant. So the output voltage V0 will be proportional to the natural logarithm of input voltage Vi for a fixed value of the resistance R1. Therefore, the operational amplifier based logarithmic amplifier circuit discussed above will produce an output which is proportional to the natural logarithm of the input voltage Vt when R1 into Is is equal to 1 volt. Observe that the output voltage V0 has a negative sign which indicates that there exists a 180-degree phase difference between the input and the output. So this is all about the logarithmic amplifier. So the next is Antilog amplifier. The Antilog amplifier is an electronic circuit that produced an output that is the proportional to the anti-logarithmic of the applied input. So the operational amplifier based on anti-logarithmic amplifier produce a voltage at the output which is proportional to the anti-logarithmic of the voltage that is applied to the diode connected to its inverting terminal. This is the circuit diagram for anti-log amplifier. The circuit diagram of operational amplifier based on anti-logarithmic amplifier is shown in a figure. इस ये हमारा लॉग का जस्ट अपोजिट है. लॉग में हमने क्या किया था, इनपुट साइड रेजिस्टेंस लगाया था और फीडबैक में डायोड. इसमें हम इनपुट साइड डायोड लगा देते हैं और फीडबैक में हम रेजिस्टर को कनेक्ट कर देते हैं. In the circuit shown above, the non-inverting input terminal of the operational amplifier is connected to the ground. It means 0 volt is applied to its non-inverting input terminal. According to the virtual short concept, the voltage at the inverting input terminal of the operational amplifier will equal to the voltage present at its non-inverting input terminal. So the voltage at its inverting input terminal will 0 volt. So the nodal equation for inverting input terminals node is minus of IF plus 0 minus V0 divided by RF is equal to 0. So we get the value of V0 is equal to minus of RF into IF, equation number 4. We know that the equation for the current flowing through a diode when it is in forward bias is given below. So the IF is equal to Is into e to the power minus of Vf divided by n into Vt. Substituting the value of IF in equation number 4, so we get V0 is equal to minus of RF in bracket Is into e to the power Vf divided by n into Vt. So V0 is equal to minus of Rf into Is e to the power minus of e to the power Vf divided by n into Vt. This is equation number 5. Now the KVL equations at the input side of the inverting terminal of the operational amplifier will be Vi minus of Vf is equal to 0. So we get Vf is equal to Vi. The KVL equations at the input side of the inverting terminal of the operational amplifier will be Vf is equal to Vi. Substituting the value of Vf in equation number 5, we get V0 is equal to minus of Rf into Is into e to the power minus of e to the power Vi, not minus, e to the power Vi divided by n into Vt. Note that the above equation, the parameters n, Vt and Is are the constant, so the output voltage V0 will be proportional to the natural logarithmic of the input voltage Vi for a fixed value of feedback resistance Rf. Therefore, the operational amplifier based on anti-logarithmic amplifier circuit discussed above will produce an output which is proportional to the anti-natural logarithmic of the input voltage Vi when Rf into Is is equal to 1 volt. Observe that the output voltage V0 is having a negative sign which indicates that there exists a 180-degree phase difference between the input and the output. So this is all about regarding anti-log amplifier. The next topic is references. So these are the references of this presentation. And thank you for watching this video.